Prestack signal enhancement via local coherent summation. So there are many reasons for signal enhancement. Yeah? The simplest reason probably is just to increase signal-to-noise ratio, like what we are doing normally in the seismic processing. It can be also a reason to increase particular type of signal, let's say reflection versus multiples, or reflection versus diffractions, or opposite. So everything is depending on what we call for our particular task a signal and what we consider as a noise. So in any case, signal enhancement can be considered and is in fact a filter. And the purpose of any filter is to remove unwanted components from recorded data and to enhance the component what we consider in a particular task a signal. The effectiveness of a filter is determined by the information available about the properties of the signal and noise. So if we want to increase a signal, the best way is to know some particular characteristics of this signal. So it can be, for example, temporal or spatial spectral properties, statistical distribution, frequency content, and so on. So if we look at our seismic signal processing and signal enhancement, normally we use information about the signal or about even the subsurface model. So this is probably the most the best way to enhance the signal if you know the model, although it's never the case. And normally we want to increase signal-to-noise ratio before we build the velocity model of the subsurface. So we use in general other characteristics of the signal, like frequency range, phase or amplitude spectrum, the form of the signal. And if you look at many of signal enhancement procedures, you will find that they are based on the assumption that the move-out correction is already applied. So our signal is flattened. Yeah. So all this is a very good ideas and very efficient, maybe algorithms, but we need to know sometimes too much information about the signal. So what I'm going to tell you today, or we will discuss today, is the way to enhance the signal when we don't have this a priori information, and we have some minimal a priori information, and we make minimal assumptions. So the only assumption what we will use is assumption that our signal is spatially coherent, has a special coherency, and even not in a global but in a local sense. And its special behavior can be described by an arbitrary, continuous, and smooth function. In fact, you know, when you think about this, what I call assumption is even not an assumption. It's just a essence of seismic method. Because if we don't have seismic signals which are spatially coherent and which cannot be described by smooth, continuous function, the seismic method wouldn't work. But this is probably another issue, and we will not debate and discuss this point. So the method I'm going to describe you and to discuss with you of signal enhancement is connected in some way with a method which is called in our industry CRS, Common Reflection Surface Method. And just to facilitate the understanding, I will very shortly describe the main features of this CRS method. So if we look at this very simple 2D case, when we have depth and time at the same picture, we have a depth model, midpoint. This is the horizontal axis, midpoint numbers, or just the stations on the surface. On the y-axis, we have an offsets. We have some arbitrary structure, which is not important in our case because it's model independent method. This method will be only data dependent, and this is the strongest point of this particular signal enhancement. And we, with the blue color, you can see the full travel time, arrival times surface, yeah, which is midpoint offset function of midpoint and the offset. So if we knew the model, and with some kind of ray tracing or travel time calculation, we can know the travel time surface, the blue one, yeah, then there is no problem, and we can stack up optimally the data and to have whatever you want, time imaging, depth imaging, and so on. But this is not the case. Here with the blue color, it's shown a very smooth and hyperbolic type of the travel time surface. But in fact, for the complex models, it can be quite complex and non-hyperbolic move-out correction. So what happened in a conventional CNP-based method? We use the particular point, CDP point, just this purple line, which shows us the traces which belong to a particular CNP method. And of course, we are familiar with this method, and we know how CNP method works. The CRS method can be considered as a generalization of the CNP method, and the green surface, the green travel time surface, shows us the CRS supergather, in fact, which is a data which we approximate with some CRS hyperbolic travel time surface, which we stack instead of stacking along a particular CNP curve, we stack along the green surface, which is a time surface, which is just includes much more traces than the CNP. Yeah, this is the general scheme of the CRS-based scheme. Is used to produce zero offset, and in 2009, Dirk Gajewski and Mike Bayukov, they proposed to use this idea to enhance Prestack seismic data. So this stacking chart shows us the difference between the CNP method and the CRS method. Yeah, the CNP. So here the coordinates is a short coordinate is a vertical axis, and receiver coordinate is shown on the horizontal axis. So for a particular CNP point, CNP position, which is shown here as this square, purple square, the traces in a particular belong to the particular this CNP position are shown by purple crosses. And you see that it's only a limited and very small number of traces which can be used in a CNP method. In the CRS method, you can use the move-out correction allows us to use and coherently sum, coherently stack arbitrarily distributed shot receiver positions, which are shown here with a green color. So the aperture of the summation is much larger and much more traces included in a coherent summation. in some sense, or in this sense of aperture, it's similar to migration, when we consider that each trace contributes to a particular imaging point. In the CRS method, it's not only the CNP based traces contributing to the particular CNP zero offset trace, but many other traces which are in some vicinity of the particular CNP, they contribute to the CNP method. So this is when we consider the CRS method to produce the final zero offset section. So what here you see the CRS move out correction formula, or in fact the travel time approximation, which is, as you see, second order approximation, which can be obtained by just Taylor expansion of the travel time, similar to what we do in the CNP. And in this sense, the CRS is just a generalization of the CNP method. Yeah. This curve is this surface is parameterized by three unknown parameters: 2 radius of curvatures and emergence angle. This is the physical interpretation of the CRS method. These 2 radius of curvatures, they have also very interesting and important physical meaning, and can be interpreted as a so-called RNIP, radius of curvature for normal incident point waves, and Rn, which is the normal wave or exploding reflector wave. So if the reflectors explode, you put this exploding reflector and you have these characteristics. So we used this idea of CRS travel time surface approximation for local second order travel time signal enhancement. So what is the difference is that we introduced a local travel time approximation around an arbitrary, not zero offset, not the imaging point, but arbitrary common offset point and arbitrary sample. So this in this picture, you see the point A, which is the arbitrary trace and arbitrary sample, and the brown surface around this point shows us a small vicinity of this point, which can be described by the second order approximation. And this is not an assumption even, because this is just a fundamental mathematical fact that the function can be always accurately described in some vicinity of any point just using Taylor expansion. So if we take this Taylor expansion and we limit ourselves only to the second order approximation, in fact, we have what we need to describe the vicinity, the travel time vicinity of any arbitrary trace and any arbitrary sample. And after doing this, we have a surface which can be described, second order surface, which can be described with 5 parameters, first order and second order, when the axis X and Y in this case is CDP number and offset. And the unknown parameters, it's just a coefficients. Even we don't need to give to them any physical meaning. It's just, we can consider them as a coefficients of this second order polynomial. It's A, B, C, D, E. Yeah? E is the 5th, which is the mixed derivative between the 2 axes, X and Y. Now, if we can extract, or if we extract this, estimate this unknown 5 coefficients from the data, and we can do it in a moment, I will tell you how, we can, in fact, coherently stack the data in this vicinity and put the result and assign the result to the point A. And what is point A? It's a particular trace and particular sample. So in this way, going for every trace and every sample, we can locally enhance by coherent summation, the signal to noise ratio. When I emphasize the coherent summation, it is different from just mixing the traces, which is very simple to do, and we do it sometimes for different reasons in data processing. Yeah, here it is much more deeper in the sense that before this summation, we have to estimate these 5 parameters, which describe, in fact, the local dip and local curvature of the travel time surface. Of course, this vicinity depends on the complexity of the model. And in this presentation, of course, I will not give you a recipe how to choose this vicinity. But qualitatively, I can tell you that it's a very small vicinity. It's enough to have, let's say, 5 traces left, 5 traces right in the CNP domain, and 5 samples in the offset domain, up and down, and then we have 10 by 10. It's a very small vicinity, but we have 100 traces which we stack before any processing, yeah, at the stage of signal enhancement. Of course, if you go to mathematicians and you tell them that you need to estimate 5 parameters, it's not a big deal. Yeah, we are very conservative in geophysics, and we know very well how to estimate 1 parameter in velocity analysis, 2 parameters sometimes, and nobody wants to estimate 5 parameters. We consider this as a very heavy computational procedure. Although today, I believe we can very efficiently estimate these 5 parameters simultaneously. What we implemented is a strategy which is what we call 2 + 2 + 2. So we estimate separately 2 parameters in one direction, 2 parameters in cross-line direction, and the 5th parameter, which is the mixed derivative. This scheme shows you again what I already explained. How do we do the signal enhancement? The important point here, which was introduced by us several years ago, is so-called operator-oriented approach. Instead of estimating these 5 parameters for each sample, we implemented another scheme. We defined in the data space 2 grids. One grid is very sparse or sparse grid, which we call parameter grid, which is described here with this brown surface. And we estimate these 5 parameters not for each trace and each sample, but on a sparse grid. It's similar to how we do in Kirchhoff migration. We don't calculate travel times for every point. We calculate it on a sparse grid, and then we do interpolation. Here is a similar idea, that we estimate the operator, the curve, the surface on a sparse grid, and then we define the target grid, the summation grid, which is shown here in the yellow, and we stack these operators only in the small vicinity of the target trace, which is shown here by green, color. So one thing or one reason to do it, and the motivation was, first motivation was to save computational time. But finally, we discovered that this trick or this strategy has another very important feature, is because it's partly resolves the conflicting dips in our Prestack data. Why it happens? Because many different operators can cross the target sample, because the operators are estimated on a sparse grid. I will show you in a minute how it's happened. But before, I will show you how we estimate these 5 parameters with the strategy of the strategy of 2 plus 2 plus 1. Yeah. Why it's 2 plus 2 plus 1? Because we have 2 unknown parameters in x direction. X direction is the, let's say, inline directions, 2 parameters in y direction, in it's b and d, and 1 parameter is a mixed parameter which we estimate separately. So first we estimate parameters in cross-line direction, 2 parameters in inline direction, and finally we estimate the 5th parameter as a mixed derivative between these 2 axes. Yeah, this is our strategy, how to estimate these parameters. How to estimate these parameters? You can do a similar scheme like what we do with the velocity estimation. It's just semblance maximization. So you just do a search of these parameters and you choose the parameters which provide a maximum value of semblance or similarity. Now about the conflicting dips. You see this scheme is shown here. The blue lines show us traces, parameter trace, where we estimate the velocity, the parameters, yeah, the blue lines. And the red line is the target trace, and the red dot is the target sample. So you can see in this scheme, which is a operator-oriented scheme, if we have a conflicting dip, like in this situation, we estimate this the events parameters, dip and the curvature, separately using parameter traces. And when we do summation, then both operators, these green lines, they are crossing the target sample. This can be, like it's shown here, only 2 operators, but in practice, when you analyze how many operators can cross the target sample, you will find out that it's 10th and sometimes hundreds of operators they are crossing each target sample, and it means that at least partially we can resolve the conflicting dip situation, which cannot happen so easily and so naturally if you do estimation for each sample. If you do estimation for each sample, then you have to do a special strategy to estimate several operators separately for each target. In our operator-oriented scheme, it happens just almost automatically. Now, in fact, I described you the algorithm of our coherent summation, and we use this coherent summation for a purpose of signal enhancement. So this formula can describe this situation, which is just summation over some aperture with the shifts, with the travel time move outs, which is described here as a delta t, and W is weights, because this summation can be also weighted summation depending, for example, on the distance between the imaging or target sample and the summation trace. Now let me show you several examples how it works. This example, of course, it's an extreme example when the original data is just very low signal to noise ratio. You can see nothing. It's land data, of course, with topography and so on. But after our signal enhancement, which is shown on the left-hand side, you have gather, which will be processed for velocity model building, on migration, stack, and so on, which looks absolutely in a different way. And it's nothing, so we did not nothing but this local coherent summation. And you see that the non-hyperbolicity doesn't matter in this scheme, because we estimate parameters locally and not globally, and our summation aperture is very small. It can be 5-7 traces only left and right, and in offset direction as well. But as a result of summation of hundreds of traces, you have this signal to noise ratio enhancement. This scheme was taken by different research groups and the institutions, companies, and was developed as a commercial product or in-house product for signal enhancement. The most probably advanced product was created by Aramco and was published, and I will show you examples taken from the publication. This is Aramco, Saudi, and the group of Andrei Bakulin, together with a research group from Novosibirsk, developed a very efficient and powerful scheme for Prestack signal enhancement. But I will show you examples not only from this company, but from other companies as well. So in the up row, you see the original data, and here the data quality is quite good. And the down and the bottom, you see the results of this signal enhancement. Of course, what you see here on the left-hand side is it looks too smooth, too synthetic, I will say, view, but it's not necessary to bring it to this. It's done only for illustration purposes. This is more interesting example from Aramco, from the paper published in Geophysics, when you have a very good quality of the data without any enhancement. And this can be short gather or CNP gather or receiver gather or other domain. In the middle panel, you see the enhanced gather, and in the right-hand side, you see the difference. And you see that the difference is mostly contain the incoherent noise. But of course, using this approach, this procedure, you can as well damage a little bit the coherent events as well. The same scheme can be used not only to enhance the data, but to interpolate the data, because the output grid is not connected to the input grid. Here you see common offset section with a low signal to noise ratio and gaps between the traces. And here, this is the result of signal enhancement and trace interpolation, which is the same procedure. Yeah, if you compare it, of course, you see the very dramatic enhancement of the signal, and you fill all the small gaps between the traces. Very nice results you can observe if you look at the time or depth slices, yeah, of migrated data. For example, here I show you the before signal enhancement, some inline crossline slice, which can be depth or time, I don't remember even. And this is the same slice if you do before migration signal enhancement. Next example is even more dramatic, and you see the slice where practically the signal is not can be not observed after Prestack signal enhancement or pre-migration, of course, signal enhancement. You have absolutely beautiful depth slice. Another examples, so I have different examples from different areas and different situations. This is, I found a very interesting example from the Yamal area from Russia, where the noise is mostly caused by the ice. Yeah, these are the winter observations on the ice, and here you see the before enhancement data and after enhancement data. And on the stack level, it looks like this. Upper is before enhancement, at the bottom is after enhancement. Very important point is to choose the data domain where you want to use the signal enhancement, especially it's in a 3D situation when you have azimuthal data. So here you can use the same scheme or very similar scheme for common shot, common offset domain. It depends on your application, which will come after enhancement. If it is common shot migration, then of course you want to enhance data in common shot domain. If it is common offset migration, like Kirchhoff migration, then you can work in common offset domain. Aramco guys, they use the cross spread to preserve the best preservation of the azimuths and to have the most uniform distribution of the traces. They choose to use cross spread domain for signal enhancement. The most important or the crucial point here in the scheme is that your travel time curve, your travel time surface should be parameterized by 5 parameters, by second order surface. And then the data domain depends on which application you want to use after this signal enhancement. So more examples, and you see that the differential section contains mostly the noise. So this is signal enhancement, of course. What it's doing is noise reduction, strong noise, uncorrelated noise reduction. And at the end, I want to show you additional approach which you can use additionally to this local summation is phase preservation. The reason to use phase preservation of phase-based move-out correction, like you can call it, is that any summation procedure, as you know, make a data to look with different character. It makes damage to the frequency contained. Yeah, it works like a high frequency filter. So to reduce this effect of the high frequency filtering, the so-called phase-based move-out correction is used, and the idea goes back in the Seismic, at least, to Eugen Lichman in '99. What he suggested is to compute the spectrum, the complex phase, the phase and amplitude spectrum of the original trace. Then you do signal enhancement, and you have the spectrum of the enhanced trace. And then you do replacement of the amplitude. You take the phase spectrum of the enhanced trace, phase spectrum of the enhanced trace, and the amplitude spectrum you preserve from the original trace. In this way, it looks like a trick, but in fact, it has a very good scientific explanation as well, and you can find the theoretical part of this in the work of Lichman in SEG 99. But what happens as a result of this amplitude spectrum replacement, that you keep the behavior of the input traces in the enhanced data. So in the enhanced data, you have the phase spectrum of the enhanced trace, of the stacked trace, but the amplitude spectrum you preserve as it is as it is in the original trace. And look which effect it's doing for the traces. Eugen Lichman used it for NMO correction, in fact, for AVO, to flatten the gather, yeah, for trim statics. In our case, we use it to preserve the amplitude spectrum character of the enhanced data. So left-hand side shows the original data. The middle shows the enhanced traces as it is. And the right-hand side show you the enhanced data with preservation of the amplitude spectrum of the original traces. You see that this traces or this gather looks much similar to the original data in the character, in the frequency contained, because we preserve the amplitude spectrum of the original data, but it looks much more coherent with increased signal to noise ratio. So I can define it in the following way, that we take the best from the phase spectrum, which is enhancement, and we preserve the frequency range of the original data. So we don't lose the high frequency content of the data. This is the same, but on the level of the stack or migration. Yeah. So the left-hand side is the original stack or migration. The central panel is the enhanced, and here you see we lose the high frequencies and it looks over smooth. And the right-hand side is the enhanced with the phase substitution. So this phase substitution, in fact, has the phase spectrum of the enhanced data and amplitude spectrum of the original traces. This is taken also from publication of Aramco. So in conclusion, I can say that I presented a method to improve the quality of the 3D Prestack seismic data. The method uses a second order approximation, and this is only one assumption, so it's nothing to do not with the knowledge of the model and not the information about the data characteristics. We only use the second order approximation of local move-out correction. So we can consider this method as a model independent signal enhancement method. The optimal wavefront parameters can be estimated using different data domains, and the proposed operator or oriented implementation scheme allows to resolve at least partially the conflicting deep problem. So the results on the real and synthetic data you can find now in different publications, and it is used quite widely in the industry for signal enhancement before velocity model construction and before PSDM or PSTM. Thank you very much for your attention, and sorry I probably was too long, and probably no, I'm in time, I think. Yeah, I will be glad to hear your opinion and to answer your questions.
Thank you very much, Evgeny. Perfect timing, and I'm starting to see some questions popping up in the question box. which you probably can open and see for yourself. But I will read them for everyone. Vemund Stenbeck asking, are diffractions properly handled, or are they lost during signal enhancement?
Yeah. Look, yeah, it's a very, very good question. Of course, I could and I wanted to describe this point in my presentation, at least because diffraction imaging is my favorite subject. Of course, it was a big fear, especially for me, to use this scheme and to lose diffraction. It depends mostly on the aperture and the accuracy you do in this procedure. There is no any reason that any coherent event will be damaged or will be lost, because we are not oriented to reflection, to diffraction, to multiples. I can say even more worse situation, that we increase multiples as well. We increase signal to noise for any coherent, and even I will emphasize locally coherent event. The event which we produce signal to noise improvement or enhancement should not be even globally coherent. If it's locally coherent, so we will increase only the signal to noise in this locally coherent part, but not we will not smear, or at least we will not smear too much the locally coherent event, and to make a artificial coherency. But of course, first of all, diffractions, if you do it, and I have here, I don't want, maybe if I can go back only, I have an example where you see perfectly. Let me try to do it. If I go back now, why I can't go back?
Try backspace.
Yeah. I have a perfect example exactly on this question, showing this zoomed. No, not here. Sorry. Oh, I removed it probably. Yes, I removed it probably to save the time. So the answer is certainly no, because this is one of the reasons it's not to damage diffractions. But you have to be very careful with the aperture of summation and the parameters, because the parameters, they defined this A, B, C, D, E, these 5 parameters, they defined in fact, the nature of, or the behavior of the event. It's travel time, it is travel time move out. Yeah. If you estimate these parameters badly or not accurately, then you will lose the diffraction versus reflection and so on. Yeah. But it is not a fundamental fact, or it is not the part feature of the algorithm or approach. You supposed to preserve anything which looks coherent, including bad things, or not bad things, but even including the things which are not your target. So you will preserve multiples if you don't do some special conditions for these parameters estimation. You will preserve also surface waves, and you can increase even the surface wave if you don't do a special treatment of the aperture and of the parameter range. Yeah, and diffraction, of course, I want to preserve, and this algorithm preserves diffractions as well. It can increase diffraction energy as well. Thank you.
Thank you very much. Another question is from Eric Kleiss. Yes. He's asking, how is the reflection surface method jeopardized if the reflection surface is not continuous?
Yeah.
An example, due to unresolved statics or other distortions.
Yes, yes. Thank you for the question. It's connected, in fact, to the previous one, and what I can the answer is that all the secret is in the aperture of summation. The aperture of this local summation, and this is what I try to emphasize many times, that it is not a global estimation, not a global summation, where you can lose the discontinuities. You will preserve discontinuities, especially when your aperture is not larger than the so-called Fresnel zone, yeah? Because our resolution of seismic resolution is not infinite, yeah? And what we call discontinuity, or what we consider as a fault, in fact, is a Fresnel zone, yeah? Because it's very difficult with the conventional seismic to see the features of the subsurface less than the lambda divided by 2 or lambda divided by 4. It's only if you use special methods like diffraction imaging or super resolution methods, which are not yet developed in seismic, we can really speak about some very, very, very small elements of the subsurface. So our scale, in fact, in seismic is connected always to Fresnel zone. And Fresnel zone, we know how to estimate, how to compute. We have an idea of Fresnel zones, and it's always tens or hundreds of meters. So if your stacking aperture is not larger, it's not bigger or larger than the Fresnel zone, we will not lose the discontinuity. So we preserve discontinuities as well. And non-hyperbolicity guarantee us to working with topography, because one of the reasons of the non-hyperbolicity beside the geology is the topography, for example. Of course, you can do statics before signal enhancement, but I suggest you to do enhancement as a first step, signal enhancement, with the topography, because it's a pity to do statics, which in fact damages the data. The topography is the only one thing which we can measure, in fact. We cannot measure subsurface, but the topography we measure exact. So stay on the topography, but use not large apertures in the local summation, and you will do the signal enhancement from topography. Again, in my examples, there is one where you see the shot gather from topography with enhanced signal, and the enhanced signal looks very much non-hyperbolic. And it happens because of we preserve topography, like we preserve topography. We do the enhancement from the topography. I hope it's understandable.
Yeah, thank you. If not, then Eric probably can reiterate if we'll have more time, or send an email with a particular question if we run out of time. Yes. He has another question. I will suggest you kind of try to answer it short, because we have more questions popping up. Yes, so Eric is asking, can you show results on a pre-time migrated process data with and without the coherency enhancement to demonstrate the absence of smearing? Before the migration.
Look at these time slices, which on the screen just, which I showed you, this and this. Yeah, this is before. This is it. The enhancement is done on the raw data, so it's not what you see here. It's not effect of migration, and it doesn't matter. It's depth migration or time migration. So this is a migrated image or migrated slice. This is before enhancement, and this is after enhancement. So we enhance the raw data. The result of migration will be the same. So this is done with the same velocity. So if we preserve here like discontinuities, okay, it's a question for more interpreters, but I can assure you that the most of discontinuities which are like on the scale of the Fresnel zone or lambda divided by 4, we preserve. Or here, this is PSTM slide without pre-migrated signal enhancement. And this is the same slide when the data was enhanced before migration. Okay.
Okay, so apparently there's no smearing observed.
I don't think that we have smear. Of course, no, don't idealize the situation. Of course, there is some smearing, yeah, because there is a summation procedure. Yeah, but in many cases, you will prefer this without smearing or this with smearing. This is my answer. Yeah, don't do signal enhancement when you have a good data quality. I don't suggest to do signal enhancement if you have enough for your purposes quality of the data. Then there is no reason to do signal enhancement, because signal enhancement will always do some, I can say, damage to the data. It will reduce some high frequencies. This is why this last trick of phase substitution is done, to preserve the yeah. But even if we do this, like preserving the frequency range, like substituting the phase of the enhanced data and preserving the amplitude characteristic, we in any way we will make some damage. So if you have a perfect data with a high quality, don't do signal enhancement. But if you have a data which produces garbage like this, you can try to improve this image to make it more reliable, more interpretable, on the account, of course, of some smearing. But it's a very little, it's a minimum smearing you can image. You know, the PSDM makes smearing as well, because you mix traces. And then there is no way that you don't lose high frequencies. And you make smearing, and you can lose discontinuities and so on and so on. And your model is not perfect. So this is absolutely model independent. This is data dependent. So it's data-based method. There is no any model considerations here. Okay, thank you.
Okay, thank you very much. One more from Eric. What is the key difference of your method compared to the CRS approach introduced by Hubral?
Yes, this is what I started to my presentation, that in fact, this idea comes from Hubral and from Dirgaevsky, from the CRS. It's CRS based. This is why we call it CRS based approach. The difference is that in CRS, in the classical CRS, the approximation is global. You approximate full range of offsets with a one continuous second order surface. And you bring the data to the zero offset. The final product of the CRS is the zero offset approximation. Here, what we do, we're using the same second order approximation. We do local summation for each offset. You can compare this, it's much more close to, there is a common offset CRS. Yeah. If you do common offset CRS, then this is very similar. When you do the summation for each offset separately. But the implementation here is much more sophisticated, like in common offset CRS, all this dense grid and target grid and local grid, which resolves the conflicting dips and so on. So, but you are right that in principle, the roots of this signal enhancement is in the CRS and connected to name of Hubral and Gilchinsky and Dirgaevsky and Martin Tigel and all who was working on the CRS, in the CRS and multifocusing direction. Thank you.
Okay, thank you. Next question is from Henry. Can the CRS method compromise migration in any way?
Look, it can be combined. Yeah, I would say. I will propose you a the beautiful scheme how to do it the best. But if you to answer to your question as it's formulated, it's two different animals, because CRS is a constructing of unmigrated zero offset approximation, and it means that it's a focusing method. Like migration can be considered as a two-step method is focusing and location. Focusing and location. But if you do it separately, focusing and then you do location, then it's like post-stack migration. If you have a good data and good velocity model, then do PSDM or PSTM. You can do one step, these two steps in one step. You combine this and you have the answer. But if you have a bad data or you have a bad velocity model, which is the case always, you always have a wrong velocity model. You never have a true velocity model or correct velocity model. Then if your velocity model is far to be accurate, you lose both. You lose focusing and you lose location. So migration is focusing and plus location. It's in fact migration, to put it in the correct place. This approach, CRS, and then post-stack migration is alternative. At least you can have, because CRS is data dependent. Migration is never data dependent method only. It's always model-based method. You need the velocity model. For CRS, you don't need velocity model. So it means that you can do optimal focusing. And then you do a wrong location. So in many situations, or in situations, of course, to decide is interpreter should decide what he prefers. He prefers a well-focused or optimally focused image, but in the wrong positions, or he prefers a bad image in the wrong positions. This is my answer, yeah? Thank you.
Okay, thank you. Peter Robotham asks, what you describe in the Crs method sounds like something that machine learning can do. It is a set of a convolutional neural network and let it search the data. What dangers do you see in this non-physics-based approach?
Yeah, very good question. And the machine learning is very popular today. And there is an illusion that machine learning can do everything. And maybe in 1,000 years we will have the car which is driven without a driver, but it will take time. The same, even more with the seismic. There are tasks which machine learning can do easily. For example, peaking. Yeah, this is a good or anomaly detection or attribute analysis. It's really machine learning can do a lot. But can machine learning change interpreter, or can it change the data processing or velocity model building? I doubt. But of course, the elements of machine learning can be used very efficiently in this approach as well. Yeah? To estimate parameters, to optimize parameters, to do some optimization of aperture and so on. But I'm not sure that it will be, at least today, it will be more efficient. It's interesting and very important issue for research, less practical for the moment, but I'm in favor, yeah, that machine learning can be included here, but I don't believe that machine learning can just replace everything and everywhere. It is just a wonderful tool which should be used together with deterministic methods. So I would say like this: everything you can describe as a deterministic function is much better to describe as a deterministic function and not to use machine learning. Machine learning comes in a game when determinism is gone, when you used already all the determinism. If you know that the second order approximation adequately describes the local coherent event, so use the second order approximation. If you don't know how to describe your move out correction, then machine learning can help. Thank you.
Okay, so there is a danger, but you can handle it. You can mitigate it with applying together with deterministic approaches, maybe speed up using
yes, absolutely. And the main point is that when you don't know determinism, or you take a wrong, like in full waveform inversion, when you take a wrong assumption about the equation, the governing equation. For example, the wave equation, it is a wrong equation for wave propagation in the real Earth, in non-elastic Earth. And you use wave equation wrongly to describe the wave propagation. Then it's bad to use. It's not a good idea to use determinism. Then machine learning can resolve these problems. This is why machine learning easily distinguish between dog and cat, because you don't have a deterministic description of what is cat and what is dog. Then use machine learning.
All right. Okay. Thank you. So there is like another 5 or 7 questions. So I suggest we try to answer them briefly. So Eric Kleiss is asking, is it a user-specified parameter how many intersecting coherency surfaces are fitted at any trace sample location?
Yes, yes. You can define it really as a parameter, as external parameter. Yeah, you can say not more than 25, and then it will do 25, not more. But more is better.
Okay, yeah, thank you. So Jeff is asking, for land data, are residual statics required ahead of this local coherency stacking?
A good question. If the residual stacking is doing or is a very rough function, if you have a strong residual stacking, as it is better to put it before. So the main consideration here should be how adequate, how good we describe with the second order smooth surface the real behavior of the travel time. If you think that it's enough smooth, then don't use residual statics. So, but I think residual stacking is in many cases is better to apply before signal enhancement. Or at least like what we do in Petrotrace, we try two-path signal enhancement. Like we do twice the signal enhancement, one before residual statics to help to compute better residual statics. Then when we calculate the residual statics, we do another path of signal enhancement.
Okay, very good. So if you don't know, do it twice.
Yes.
Yeah, thank you. A question from an anonymous attendee. Do you work on a sample by sample basis or with a window in time?
Yeah, good practical question. Of course, we don't work we don't work sample by sample. We have a step in samples and we interpolate between them. But this is like for practical time computational time purposes.
Okay, thank you. David Cleverly asking, what do you mean by based on partial stacks on conclusion slide? And also, would this process be recommended before FWI?
Yes. So first part, the partial stack, what I mean is not compared to or as a opposite to global. It is, so we take the stacking aperture is not all offsets together like in CNP or in CRS, but we do the limited offset from this to this and the CNP from this to this. This is the partial stack, not in the sense that we take only partial traces for this. It's a partial, it's a limited aperture stack. It's better to call limited aperture stack. Now about FWI, with all my like critical opinion about FWI, if somebody or many people are doing FWI, I would say that you should do it on the raw data. Yeah, because it's like comparison between the synthetic and the real data. This is the criterion of FWI, and you don't want to damage the data, not in amplitude, not in phase, in nothing. Yeah, and by the way, this this question shows you how limited is FWI using. Yeah, because when your data is not perfect, but really perfect, then forget about FWI. What you fit.
Okay, thank you. We move on. So it's another question which is similar to what you answered previously. I will just briefly read it.
Yes, please.
Are you aware of any convincing results using the Prestack enhancement data as a guide for surface consistent statics or phase residual corrections?
Yes, my answer is certainly yes. Yeah, in many cases, length data where residual statics is important. Yes, it is. The enhanced data gives you the good guide. Yeah, the pilot trace. Yeah, for residual static calculation. Yeah,
this is related to the length question we had previously.
Yes.
Yeah. Okay, thank you. Tim Papworth asking, how many traces are typically included in the analysis and what is the normal spatial range?
Yeah, as I said, there are two grids. Yeah, there is operator estimation, which is the sparse grid. And here you can use 20, 25 traces. Yeah, with the distance, I guess the distance between traces can be 20, 25 meters. Yeah, but the stacking, the summation, this limited offset summation or limited aperture summation, normally we take quite small. Yeah, 5, 7, 9 traces, not more. And this is neighbor traces. Yeah, but not more. But I say you can do it formally. Just it should be time or depth dependent. Yeah, time in our case, time dependent because it's a data domain, and it can be related in some way to Fresnel zone with some average velocity or something, some idea to have. So not to exceed the Fresnel zone summation. Otherwise, we will just over smooth. It's not a big deal. It depends what do we want to see. In structural imaging, for example, you don't want to see or you don't want to preserve all the discontinuities or small faults. Then you can use larger apertures. But if you want to have a reliable image, then use always the small limited aperture summation, which is 5, 7 traces in each direction.
Okay, thank you. We have 3 more questions to go.
Yeah.
Tim Seher asking, do your local stacking parameters, ABC, have a physical interpretation? Can they be exploited as attributes?
No, in this, like what we did and what I have experienced, it's better not to go too much in this direction. It's enough we have this CRS and common offset CRS where we really have a very clear and correct or real physical meaning for this radius of curvature. Here we try to, to avoid this. We wanted just a Taylor expansion, the local Taylor expansion for the arbitrary function, just pure mathematics. And it's occasionally or not occasionally, it coincides with the CRS. That CRS is also second order expansion. Just in the CRS theory, you have this physical meaning. But physical meaning is always has a opposite side, negative side, yeah, because it's too many simplifications and assumptions to really bring. There is a connection between the CRS parameters to the physics, but it's not more the connection. This connection can be non-linear and it's a very complex connection. Everything is model dependent, and we didn't want to make our approach model dependent. Physics is a model, yeah, and we wanted to be data dependent only.
Okay, thank you. Another one from Jonathan White. He's saying, to my interpreter's eye, the appearance of CRS enhanced data looks similar to data migrated with beam migration. Is there a theoretical connection between these two concepts, or is it just a coincidence?
No, yeah, very good point. Thank you. Of course, there is a connection, very clear connection between the CRS and the multifocusing and the beam migration. And it's not occasionally that Aramco group, yeah, which is Andrei Bakulin and the group, they call this method, this signal enhancement method, they call it nonlinear beam forming. Because this is a really nonlinear, because beam forming is only the deep, yeah, only the first order approximation, yeah, this is the beam, yeah, and we use not only the beam, we try to use also the curvature, yeah, this is why they called it nonlinear beam forming, yeah, but there is a very clear connection between CRS, all the CRS theory and all this, what is behind this, and the beam migration. Just one, don't forget that again, that beam migration, it's a migration, yeah, and CRS is a zero offset approximation. It's a difference between the normal rays and vertical rays in the Hubral's terminology.
Okay, very good. So we see some similarities, and it's better. It makes us better to understand what's the difference and what's similar between those two approaches. Another question from Dimitris Dimitropoulos: can this approach be used for 2D data?
Yes, for 2D it is just straightforward. This is it's much simpler because there is no azimuths. Then there is a CNP or station number and the offset. This is the two axes. And then 5 parameters again, these 5 parameters, but with the CNP number or CNP location and offset. It's another axis. And then everything what I told you, this can be done. This will be full like explosion of the exploding of the data. Yeah, in 3D it's a bit tricky. It depends on, as I said, what do we want to do with this, and then we should choose the domain. In 2D it's straightforward. You don't need to define in which domain you will do it, because you do it in a full 2D domain, because 2D data is a 5D cube. Yeah, it's source location, receiver location, point location, and the time. So you just use fully you use the full data in 2D. Yeah.
Okay.
But the scheme stays basically the same.
Okay, so the short answer is yes.
Yes.
Perfectly suitable. And the last answer we got from anonymous attendee: how does this compare with FX decon?
Opa, here you got me. With
FX decon.
FX decon. FX decon. I would
this
say,
is just coherency filter, I would say, but
yeah. I would reformulate it. What is the like an opposite way? Not what is the connection. There is no any connection, I think.
Okay, so it's not related.
Not related, no.
Okay, this is all we got in the Q&A box, and we managed well in the timing, and we are approaching 8 o'clock here in London. I cannot even imagine how late it is in Israel now.
No, it's only 10.
It's only 10. Okay, not too bad. But tomorrow is early morning with another lectures, I believe. So I would like to thank you on behalf of our EEG local chapter and on behalf of our local as well as global community. I can see some people from Europe and Russia joined our webinar today. Thank you very much. I hope so. You gave the second talk for us. I hope in a couple of years we can repeat our success. Otherwise, I want to remind to everyone who attended today that Netherlands local chapter will have their talk tomorrow. If you're interested, please go and register for their talk. And please contact us if you want to present something interesting and share your advanced and interesting results with our community. So far, as we are closed in the quarantine, we can accept participants remotely from all over the world. Please use this opportunity to show us your results. With that, I would like to close this evening. Thank you everyone for joining us and participating. And thank you, Evgeny.
Thank you. And Artyom, there is no beer.
Unfortunately, there is no AG supplied beer, but I promise when we're back to normality, we'll compensate it.
I will remember.
Yes, yes, yes.
Good. Everybody is invited.
Yes, absolutely.
Good. Thank you. Thank you very much.
Thank you. Bye-bye for now.